what you are doing is, when you see the existing vegetable vendors, what you are actually getting is the conditional mean of earnings conditional upon all those vegetable vendors who are willing to work at a less than some hour earnings per day. So what you really have is a conditional mean, whereas your question is that of an unconditional mean. These are called sample selection biases, which are very random. So as econometricians, if you run a regression with that kind of a sampling process, then you actually get wrong estimates. And so there are tests called specification tests and all that, which have to be actually run when you're doing those kinds of samples. Right? So what seems intuitively very simple, कि हमको अगर average earnings of vegetable vendors ढूंढना है तो जो भी vegetable vendors है उनका income ढूंढो. No, what you're really doing is you are putting a conditional mean on vegetable vendor. What you're really doing is you're getting mean earnings of vegetable vendors who satisfy certain conditions, i.e. who are willing to work in the market at a rate less than a certain quantity. Yeah, suppose the vegetable earnings, so tomorrow if the situation changes a little bit, then I might want to become a vegetable vendor and I might actually earn more than the current vegetable vendors, so the averages might change a lot. Right, so therefore designing sample is a designing samples becomes a very complex and exercise which requires a lot of thought. Right, so I can't, for example, if you finding out how much is an existing Vodafone user, how much will a person be willing to pay for a certain kind of a Vodafone package? You can't go only to Vodafone customers, because then you get the mean conditional on the person being an existing Vodafone user. Whereas your question is, how much will a person be willing to pay, which is an unconditional statement. So you must be very critical in distinguishing between conditional means and unconditional means that you want to get. Right? Okay. So that's a very important question, and in any case, if your x1, x2, x3, x4 are all related to each other, right? For example, if you only go to your friends for your information, then obviously your friends are all common friends, so their earnings must be reasonably correlated with each other. So in which case you're not going to get x1, x2, x3, x4 independent of each other, not going to get them independent. This formula is not going to be derived, and therefore this is all going to go for a toss. That's just very important, that the samples that you get. For example, some of my PhD students engage their students to do surveys. So they might do something on insurance buying behavior, and you have somebody in college who's doing a PhD with me. Then what that person will do is, that person will go and give questionnaires to all her students and get them to fill those questionnaires up from their relatives. Right? This is non-random sampling, because people who are not friends of your students have no chance of appearing in the sample. Right? More importantly, you might have your friends, right? Your students' friends might all come from the same socio-economic stratum, in which case there will be high correlation between the answers that you will get. So the questions will all, the survey will not, so whatever the survey is, you can't use these ideas, because then this formula can't be derived. Right? So these are something which you must remember. Therefore, whenever you are given any data to work on, an important question is to ask, who's collected the data, how have the data been collected, from where do the data come, what have been the methodologies. Unless you are very, very clear about how, through what channels, through what methods have the data actually come to you, you can't really design a statistical method. So your understanding of your data sources must be very, very clear. Right? So if you are an economist using data on national income, you must very clearly know from where the data have come, how have they been calculated, what are the various assumptions that have gone into the data that you've got. It's not enough to simply run a regression on that data, right, without knowing. And if you look at market research market surveys kind of data, if you ask all kinds of questions, they will see lots of skeletons come out of the closets. So it's always important to make sure that those kinds of data are interrogated very well.
Sir, I have one question. So while we are collecting this data,
right.
So I'm trying to design a model.
Right.
Okay. So you talked about asking different questions. So I'm working suppose in a particular domain. To my knowledge, I have the best understanding, but there might be few things that I don't know. Okay. And then how this errors can be covered up by designing the model.
see, I think the best possible solution is first to know everything that there is to. So that's very important. As somebody who's using statistics, as somebody who's a data analyst, especially somebody who's developing models using data analyst, you cannot work in isolation in your organization. You must have a very clear dialogue between who are the various stakeholders at various decision points. Okay? And then get an overall holistic understanding. Make sure that nothing is left out. But if you doubt that something is left out, and if you know that there is a significant gap between what is valid, what is required for this technique to be valid, and what you have, then try to see if there is any other technique that can be used. But give this technique up. So the whole idea really that we are trying to develop in this course is this ability to think, now this technique will not work, I need to use this. Right. This might not work, this I need to use. But if I use this, these are the pros, these are the cons. Right. That is the kind of thinking about data that is going to happen ideally in this course. Right. So is that okay? Now, suppose we have something which you guys must have heard a lot about. I said, so think of 0.95 is the probability. So suppose X bar comes from a population with mean, mu and variance sigma square, then I know probability less than or equal to X bar minus mu by sigma by root n is equal to 0.95. Right? I can change this to write probability X bar minus 1.96 sigma by root n I can write it like this. So this was X bar. Yeah? So I've taken X bar on this side, X bar minus 1.96 into sigma by root n. So first I multiplied sigma by root n on this side, sigma by root n on this side. I got minus 1.96 plus 1.96 sigma by root n, and then subtracted X bar from both the sides. So I got X bar minus 1.96 sigma by root n, X bar plus 1.96 sigma by root n as two boundaries and mu lying between them. Now what is say?
Sorry, if you had subtracted X bar, then it would have been 1.
If I subtracted X bar, then it would have been, so if I take X bar here, minus 1.96 sigma minus X bar. Right? So this can be written as minus X bar plus 1.96 whatever sigma by root n. Right? Okay. Which I can write as, so basically what I did is, yeah, you're right. So minus 1.96 sigma by X bar, and so basically what I did was I did something quite ulta sulta here. Missed out several steps in between. Okay, let's do one thing. Let me add X bar here. Let me also add X bar here. Okay. So what do I get?
First we multiply by
Yeah, so first we multiply by minus 1 sigma by root n. So I'll get probability minus 1.96 sigma by root n X bar minus mu less than or equal to 1.96 sigma by root. Right? Okay? Now let me subtract X bar from all sides. So what do I get? I get minus X bar minus 1.96 sigma by root n minus mu, right? Minus and plus 1.96 minus X bar. Right? Okay. Now let me multiply this by minus. So what do I get?
X bar plus.
X bar plus 1.96 sigma by root n, but the inequality will become reverse. Right? So this will become plus mu plus X bar minus 1.96 sigma by root n, which is this. Yeah, which is this, which is where? Yeah. So basically, okay. Is this clear? So it means that I write this as essentially. So what it says, now this is a very important statement. So you write it as 0.95 See, this is very important because what is x bar? X bar is an estimate of mu. You do not know what mu is. Right? So what you are effectively saying, you know what is x bar. You can measure it from the sample. You know what is sigma, what is root n. So what you are really saying is, even though I do not know mu, I can create some confidence in some interval around x bar, which is my estimate. So x bar is my estimate. X bar is different from mu. Right? But I am saying that there will be an interval around x bar in which mu will lie 95 times out of 100. So what I am creating is an interval, confidence interval for mu. Right? So for example, if I find in this set that x bar is equal to 10, sigma is equal to 2, root n is equal to 4, right? Then what I am saying is, though x bar is my estimate of mu, and I do not know mu will lie between 10 plus 1.96 into 2 upon 4 and 10 minus 1.96 into 2 upon 4. Right? So this is 10 minus something, 10 plus something. So I am saying there is an interval in which the true value of mu will lie 95 times of 100. So if I take 100 samples like this, if I create 100 such intervals around that, 95 times those intervals will contain the true value of the population. True value of mu. Right? This is called a 95% confidence interval around mu. Right? So I don't know what mu is, but it allows me to say that mu will lie between this range. 95 times out of 100. Okay? That's how you create a confidence interval. And what does the confidence interval depend upon? Do you like wide confidence intervals or narrow confidence intervals? Yeah, but ideally what would you like to have? Would you like to have confidence intervals which are very wide? You would like to have them as narrow as possible, no? So this is my estimate, and the actual value lies in a narrow estimate, narrow range around this estimate, rather than saying that this is my estimate, but the actual value can lie anywhere in the wide range. So you want as narrow an estimate. Now tell me, what does that narrowness depend upon?
N.
It depends upon n.
Yes.
So as n becomes large, what happens to that estimate?
It becomes narrow.
It becomes narrow. Because sigma by root n. Root n increases, so this becomes narrow. It increases with sigma. Can you interpret that? In terms of my weighing scale example, what does this mean? In terms of a weighing scale example, reliability goes down. So, I've got this sack here. I do not know what the weight of that sack is. I've got a scale, which is some variability, but not very high variability. If I put that sack and say it says I am getting a reading of 90 kilos, but the actual reading is between say 10 grams here and there between 90 kilos. Because the variability of the scale is not high. The scale was very variable. If I put my on that, I'll again say that 90 kilos is the reading, but the actual weight can lie anywhere between 120 kilos to 50 kilos because the scale is very variable. So larger the variability of the measurement, okay, wider will be your confidence intervals. The larger the n, smaller will be your confidence intervals. And this idea is going to be very important when we do forecasting. Because when you are actually forecasting a quantity, everybody knows that your forecast is actually a point estimate. Your forecast will not be exactly that. The actual will not be exactly that, but the actual quantity in the future will lie between some range from that forecast. So you should be able to create that range. These are called confidence intervals for forecasts. Okay, these are called confidence intervals for forecasts. Okay,
To the larger the variability,
the wider the confidence interval, the larger the variability, wider the confidence intervals. Right, so dirtier are your instruments, the less reliable is your reading, no? Yeah, that's really sure. So we'll stop here today. We have to do something on a different distribution, etc. from the next class. But everyone understood the Z distribution and this whole idea of p-value, one-tailed test, two-tailed test, confidence intervals. Yeah, then we've understood a lot. So let's stop here today, and then I'll go and immediately put these up on the